Hello dear students, myself Mohammad Wasim, Assistant Professor in Mathematics, Art Science, Commerce College, Badnapur. In previous lecture we have seen about the Laplace transform, in which we have learned about the definition of Laplace transform and we have studied about some basic function. With the help of Laplace transform we have found the Laplace transform of the basic function. We have seen about some theorems on Laplace transform, and now we will see some special type of examples which will use a specific theorem to solve, and the statement of the theorem is the Laplace transform of t into f of t, and the resultant value is, or we can say that t raised to n into f of t is equal to minus 1 raised to n dn by dsn of f of s. Correct? We have to use this formula to solve example, and we can see here, we can see that when function has multiplication of the variable t, then we will use this type of equation to solve the example. So we will start with the first example, and the first example is as follows. The example 1 is find the Laplace transform of the Laplace transform of that is t into sine 2t. As the theorem says, function with the multiplication of t having any integer value of power of t is there, we will get minus 1 raised to the power of t, that is n, and find the Laplace transform of f of t, find the Laplace transform of f of t, and differentiate n times to find the actual solution of this example. We can see here no power is given, means we have 1 in the power of t. So t raised to 1 into sine 2t. So we can write it as minus 1 power of t is 1. So minus 1 raised to 1 d raised to n is 1 here. So d raised to 1 ds raised to 1 f of s. And what is f of s? F of s is a Laplace transform of this f of t. Since f of t is given as sine 2t, therefore Laplace transform of f of t means Laplace transform of sine 2t is equal to 2 upon s square 2 square. Since we know that Laplace transform of sine at is equal to a upon s square plus a square. Friends, remember one thing: whenever a function comes with the multiplication of variable t having any power, then such type of function can be take Laplace transform and gives us the formula minus 1 raised to n dn by dsn of f of s. So we have to calculate f of s first and then the differentiation of that function. So we are finding here Laplace transform of sine 2t, and we get Laplace transform of sine 2t is equal to 2 upon s square plus 2 square, and when we multiply by differentiation of 2 upon s square plus 2 square. We can solve it by using u upon v form. We can solve this differentiation using the u upon v form. First of all, take denominator outside, differentiation of numerator, and minus taking numerator outside, differentiation of denominator upon denominator square. So we can write it as s square plus 2 square d by ds of 2 minus taking 2 outside d by ds of s square plus 2 square and upon s square plus 2 square bracket square. Correct? Now we can solve it easily. We will get denominator as it is, s square 2 square bracket is to 2 s square plus 2 square, and differentiation of constant number becomes 0, so we will get 0 at the left hand side minus 2 as it is. Differentiation of s square becomes 2s, and differentiation of 2 square, since 2 square is 4 and which is constant, so we can write it as 2s plus 0 minus 1 as it is. Minus 2 into 2s become minus 4s, s square plus 2 square bracket is 2 square, and minus become plus 4s upon s square plus 2 square bracket square, and it is the Laplace transform of t sin 2t. Right? We have the result 4s upon s square plus 2 square bracket square. First of all, understand what is the statement of theorem say. Whenever we want to find the Laplace transform of such function in which two functions are in multiplication, while one is in the form of variable t, which is in multiplication of any function f of t, so we will get minus 1 as the power of t is n, so we can write it as minus 1 raised to n d by dsn, means differentiation n times of f of s. First of all, we have to calculate the value of f of s, means we have to find the Laplace transform of only f of t. When we get the Laplace transform of f of t in the form of f of s, then we can differentiate n times to that function and we will get the required result. Now we will see another example for the same type of example. And the example is as follows. We have to find the Laplace transform of t hyperbolic cos at. We have to find the Laplace transform of t into hyperbolic cos at, and since the power of t is 1, we can write it as minus 1 raised to n minus 1 raised to 1 d by ds of f of s. And first of all, we have to calculate the value f of s, and since we know that f of s is equals to Laplace transform of f of t, and f of t is here cos 80, and we know that the Laplace transform of cos 80 is s upon s square minus a square. Since the Laplace transform of cos 80 is equals to s upon s square minus a square, we have already deduced this result with the help of exponential function. Now, since here we have to find the first derivative, so Laplace transform of t cos 80 becomes minus 1 raised to 1 and d by ds of s upon s square minus a square. I think it is easily understandable. It is very easily. Now find the differentiation of s upon s square minus a square. So we can take denominator outside, s square minus a square, and differentiation of s with respect to s minus taking numerator outside and differentiation of s square minus a square, s square minus a square bracket square, and it is clearly understandable that we are using a u upon v form. So minus 1 into s square minus a square, differentiation of s with respect to x become 1. So we will get s square minus a square minus s, and differentiation of s square minus a square, differentiation of s square becomes 2s, and differentiation of a square when a is constant, we will get 0. S square minus a square bracket square. So we will get minus 1 s square minus a square minus 2s square upon s square minus a square bracket square, and we will get minus a square minus s square minus a square bracket square, and putting this minus inside of the bracket, we will get a square plus s square upon s square a square bracket square, and it is the required result of this example. First of all, see what we have did with this example. First of all, we have correlate this example with this theorem, and we can see that whenever t has power 1, the resultant Laplace transform is minus 1 raised to n differentiation of f of s with respect to s one time, because we have only 1 in the power of t. To find this value of the right hand side, we have to calculate it. We have to calculate f of s first, means Laplace transform of f of t first. And after finding the Laplace transform of f of t, we will get the Laplace transform of f of t is s upon s square minus a square. Therefore, f of s becomes s upon s square minus a square, and after putting this value in this equation, we will get this result a square plus s square upon s square minus a square bracket square. Now, I think it is easily understandable. Now we will see one more example. With now we can see a Laplace transform of t cube, Laplace transform of t cube e raised to minus 3t. Since we are studying about the theorem in which we are taking Laplace transform of such function which has f of t and t raised to n in the multiplication of with f of t. So we can take e raised to minus 3t as f of t. So Laplace transform of f of t means Laplace transform of e raised to minus 3t will become 1 upon s plus 3, and we can say that it is f of s. And since we have t cube, therefore Laplace transform of t cube e raised to minus 3t will be minus 1 raised to 3. Remember, we have 3 in the power of t, so we will write minus 1 raised to 3, and differentiation with respect to s 3 times 2 f of s, and we have f of s is equals to minus 1 raised to 3 is minus 1 into differentiation of 1 upon s plus 3. Correct? And differentiation is up to 3 times. So d by ds of 1 upon s plus 3 becomes minus 1 upon s plus 3 square. By using u upon v form, d by ds of 1 upon s plus 3, this is numerator and denominator, taking s plus 3 outside, and differentiation of 1 minus taking 1 outside, and differentiation of s plus 3 and s plus 3 bracket square. Differentiation of first number becomes 0 minus 1 as it is, and differentiation of s is 1, s plus 3 bracket square, and we will get minus 1 upon s plus 3 bracket square. Now again differentiation, taking differentiation of this one, 1 upon s plus 3, we will get minus, taking minus outside, we will get 0 s plus 3 bracket square, differentiation of 1 becomes 0 minus 1 as it is, and differentiation of this we will get 2s plus 3 upon s plus 3 cube raised to 4, and correct, 2s plus 3 bracket square, so s plus 3, so minus minus become plus, s plus 3 and s plus 3 raised to 4, we will get 2 upon s plus 3 cube. And similarly we can differentiate again, we will get d by ds of d by ds of 1 upon s plus 3, which is d cube by dx cube of 1 upon s plus 3, and we can see that minus 2 as it is into 3 s plus 2 bracket square upon s plus 3 cube into 2, and we will get s plus 3 raised to 4. It is the differentiation of third differentiation of 1 upon s plus 3, and we have the value of this with minus 1. So we can write it as the Laplace transform of t cube e raised to minus 3t becomes minus, and this minus becomes plus 6 upon s plus 3 bracket raised to 4. Correct? Now we can write one more example which is somewhat or. First of all, or we can solve this example with another method also. And the method is as follows. If we take the Laplace transform of t cube, you know that Laplace transform of t raised to n becomes n factorial s raised to n plus 1, and it becomes 3 factorial s 3 plus 1 becomes 4, and 3 factorial becomes 6 s raised to 4, and Laplace transform of e raised to minus 3t t cube becomes 6 upon s plus 3 raised to 4, and both the results are same. So we can solve it by this simple method also, and we can solve this by using the statement of theorem. And last but not the least, the Laplace transform of not the least, Laplace transform of t e raised to at sin at. Now since here we have t with minus 1 d by ds of f of t, so we will get f of s, and Laplace transform of e raised to at sin at is the first theorem. So e raised to at and it becomes gt. So Laplace transform of gt means Laplace transform of gt means sin at, a upon s square plus a square, which is g of s, and when we put in this equation sin at, so we will get a upon s minus a square plus a square, and we will get s square 2sa plus a square plus a square, and it becomes a upon s square minus 2sa plus 2a square. Correct? And it is the Laplace transform of e raised to at sin at. And last one, the remaining t. So Laplace transform of t e raised to at sin at, we get minus 1 raised to 1, and d by ds of this f of s, which is equals to a upon s square minus 2sa plus 2a square. So we will get minus 1 on this side, and denominator first and differentiation of numerator, and a is constant, so it will give us 0, and taking a outside, and differentiation of this 2s minus 2a upon s square minus 2sa plus 2a square bracket square. So we will get this minus and minus into plus. So we will get 2sa minus 2a square, and it gives us 2sa plus 2a square plus 2 square, and we can take outside 2a, so s minus a upon s square minus 2sa plus 2a square, and it is the required answer. So by the use of this theorem we can solve many examples using the statement of theorem, and it is enough example to understand the Laplace transform. In next lecture we will start with inverse Laplace transform. In inverse Laplace transform we will reverse the formula, and we will have the transformation of particular function f of s, and we have to find the inverse transform of this given function. In next lecture we will start with the inverse Laplace transform. Till then, thank you.